electricity is a really easy one describing plumbing. And so here I have in the screen in front of you, I have three sets of tubing, right? Three sources, and three of their pipes. So here we are. This is a large one. We have a big one here, a medium here, and a small there. So this is what we have. Electricity involves three main ideas. We'll be looking at three main ideas, and they are current, voltage, and resistance. In order to understand their relationship, we're going to look at these big, medium, and small water sources and installations to examine how these three things are related. The first one is current. And when you think of current like in a stream or in a river, you think of how fast, when someone's a fast current is, there's lots of water flowing through. Now, if you look through here, which one is there more water flowing through? Is there more water flowing through a bigger pipe, the medium pipe, or the small pipe? Well, obviously, there's more water flowing through the bigger pipe. And all this means is that there's more gallons of water passing through a specific point at a given time. Say that time is 1 second. We can agree that there's more gallons of water going through that 1 point per second. So we'd say 50 gallons per second, 25 gallons per second, 10 gallons per second. That's a rate. Agreed? So what we're discussing here is the definition of current, and the definition of current really simply is the rate of course, that's water. So let me step back and say we understand current because we're used to dealing with water. But current and electricity, as we learned in electricity in the other videos that we learned, is the flow of electrons. So if the electricity is the flow of electron, then current is the rate of flow of electrons. The rate of flow of electrons. And it is measured in amps. So the variable or the symbol for current is going to be the letter I. And the unit for current is going to be the unit amps. Okay, so I would say I of current equals 4.5 amps. That's how you would say that. It equals 4.5 amps. So the rate of flow of electrons was what current is, just like the current in a river is the rate of flow of gallons of water. And what an amp is, if you're curious about what an amp is, we measure things in amps. What an amp really is how many it tells you how many electrons there are. So what it really is, an amp is 1 coulomb per second. It's 1 coulomb per second. So OMB. 1 coulomb for every 1 second. And a coulomb is 6.2 times 10 to the 18 electrons, or the charge of electrons, however much energy an electron would bring for every 1 second. So that's what an amp is. So if something is 4.5 amps, it's 4.5 times 6.2. So you're looking at, what, 28 or so, roughly 28 times 10 to the 18, so that'd make it 2.9 times 10 to the 19 electrons for every 1 second. That's kind of what it's saying. We won't need to go in that detail, but I'm doing this for those who are curious what an amp is and what an amp is saying in terms as far as electricity, because if I say, oh, it's 1 amp, that doesn't really mean a whole lot if you don't know what an amp is. It's the number of electrons. So an amp is measuring the number of electrons that pass through a given point. So if we look over here, let's call these 1, 2, and 3. That'll be better than big, medium, or small. So 1, 2, or 3. 1 over here is going to have, would you think we have the most, middle, or least amount of ampage? Well, it has, we can agree, more electrons flowing through it at a given point. Okay? Let's call this 5 amps. 5 amps, and let's call this one 2.5 amps, and let's call this 1 amp. Of course, these aren't scalar or anything, but we can understand that These are bigger and that's smaller. So I think we have to check. Like I think we can check besides current. We know what current is. Well, what is voltage? Voltage. If you think of when I think of voltage, I think of an old Frankenstein movie where they have the guy on the chair, and they have those big towers here with little circles around it, two big towers, and they have the lever here, and they push up the dial, and then the more electricity gets going down because they've cranked up the voltage. And so they've cranked it up, and there's more electricity, more volts going towards a certain item. That's what I think of. I think of an old movie like that. And that's kind of what voltage is. Voltage, the definition of voltage, is the push or pull, the amount or push or pull. So it's the push or pull of, let's call it electricity. It's the measure of push or pull. Let's call that the measure of push or pull of electricity. And in order to understand this, you need to understand that, remember, go back to our battery where we have the positive end and then we have a negative end. And the electrons don't like negative. Remember that electrons don't like, they repel because they are negative themselves. So here are the electrons over here. And so the force is pushing this way away, and it's going around, and it's being pulled to the positive. And so the more batteries or the more volts. So if I have 3 volts, I'm going to have 3 volts being pushed and 3 volts being pulled. And 9 volts would have 9 volts being pushed and 9 volts being pulled. That's what it is. And so to get an understanding of this, let's go look at our plumbing scenario analogy again. And in this plumbing analogy, we have the tanks. So this is the, we have the tanks over here, and if we can look, my 3 tanks, I have the 1 tank, 2 tank, and 3 tank. The first tank is much larger, and there's more water. Since there's more water, there's a bigger, and I'm going to draw this with a bigger arrow. So the bigger the arrow, the bigger the force. So there's a bigger force pushing down on the pipe. So there's more, it's pushing more water through. So what's happening to the current? So if the voltage increases, then what happens to the current? Well, the current has to go faster. It means the current has to go higher. I hope we can understand that. So this is, and there's a little bit more water in here. So while this is a much smaller pipe, or in this scenario, this is going to be kind of our wire, if we can agree with that. While this one, the wiring between these two are different, the amount of water here is kind of close, but still less, right? So it has less voltage, but not by a whole lot. And then finally, we have the third one, it's the smallest amount of water, and so it's the smallest amount of force or voltage. So remember, voltage is the push or pull. So I have more push going down here. I have more, the middle amount of push in the second one and the least amount of push. So it has less voltage. And because it has less voltage, it has less current. If I were to increase, so let's increase the amount of water in here. And since I have more water in here, let's say I open up that tank and I get even more water in here. If I were to get even more water in here, I would really, really increase the voltage, which would really, really increase the current, probably to a dangerous level if that wire can't hold that. Okay, so that's what voltage is. And the last thing for this is that we understand is going to be resistance. And resistance is what it sounds like. So if you're curious, if you think that resistance is a funny idea, then don't worry, because resistance is exactly what the word means. And the definition for resistance, as you could probably guess, is the measurement of resistance opposing the voltage. The measure of resistance opposing the voltage. Now it's called resistance, and the symbol for resistance is R, but its unit is in ohms, O-H-M-S, ohms. And the symbol for that is omega. So it's the Greek letter omega. So again, don't be confused. The actual symbol is R for resistance, but it's measured in omegas. Now, to draw another comparison, so think about distance. Well, if I describe something as this is 1 meter, well, D is my distance. D is the symbol for distance, while meter is the unit for distance. R is the symbol for resistance, while ohms is the unit of measurement. I hope that's not confusing. So let's go back to our analogy over here. This is, let's call this a resistance, maybe a resistor. Each of these has one resistor. If you look at this, these are all the same size, or roughly the same size. So let's all call these 1 ohm, 1 ohm, and 1 ohm. On which pipe do you think the resistance will have the most effect? Well, it will have the most effect on the smallest pipe, because 1 ohm means more to this one than it does to the middle one, and definitely more than it does to the large one. And so it can't resist as much water because there's more water to go around it. Same thing in an electrical current or electrical circuit. So if I have a resistor in an electrical circuit and it is only, so I have an electrical circuit here, small here, resistor, resistor, and this one has 5, let's call this 3 amps, and this is 1 ohm, and this one is another 1 ohm. Well, that's going to slow it down, and that's going to mess with it, and so my volts, we could figure out the volts in a second. I know that probably will. But those ohms play a bigger role because of the voltage. Let's just figure out what that is. So that's going to be 3 equals x over 2, which means 6. So my voltage would have been 6 here. My voltage would have been 6 volts here, and 1 ohm apiece, and that will give me 3 amps. Well, the current is being affected by the resistors here. If I had another resistor here, well, then it would drop down, and there's another ohm, it would drop down my ampage to 2, because there's something else opposing that. So the more resistance you have, the less amps you have. They have an inverse relationship, you could say. Whereas voltage and current had a direct relationship. You increase current, you increase voltage. Let's look at it another. Instead of saying 1 ohm apiece, instead of saying these are 1 ohm, you could say, if these were 2 ohms apiece, 2 ohms, now my resistors got bigger, didn't they? 2 ohms and 2 ohms. Now my current is going to be 6 divided by 6, and it's going to give me an ampage of 1 amp. And we'll do the math later when we go over to Ohm's law, but just letting you know that the ampage is getting me. So what happened if I would have, so what would happen here if I took away these, let me draw those back there. Instead of having such small resistors, what if I made them bigger? And specifically, what if I made them bigger in this one right here? I got a big resistor here. Now it's a bigger resistor. So now it's no longer, and I don't have 1, I have 2. Do you think that's going to slow down do you think those resistors are going to slow down the current? I think they will. They're going to slow it down. So that's going to be a resistance, a greater resistance. So I'm going to have less current. I'm going to have the same voltage. You could say you could have the same voltage, but because you have the same push, you still have the same amount of force being brought back here. Think of like a kink. If you have a water hose and you kink it, you have a water hose here, and then you kink it here, some water may still come out, But if you kink it further back here, you give it 2 kinks, there's even less water. But you still have the same amount of water pushing back there, so it's increasing the pressure. So that's another thing to consider. So we've covered the 3 main terms, and I hope that we got them. And we're going to review them and kind of see how they're related right quick too. And they'll give us the foundation for Ohm's law, which will be the next video. So to review, we have resistance, and resistance is R and is measured in ohms. Voltage is measured in, it's V, and it's measured in volts. So it's kind of easy. I didn't actually mention that, but it's measured in V for volts. And current, back to the non-congruent lettering, is I, and it is measured in amps. Okay? So let's go look at what we said already would happen. If I increase my voltage, if I increased my voltage here, then what would happen to my amps? My amps would increase. Okay? But if I increase my resistance, my current would decrease. So you could say that resistance and current have a inverse relationship. And remember, if 2 things have an inverse relationship, that means they're going to be in an equation format, they're going to be multiplied together. So we know, so for instance, if this was going to be, if we are saying our volts are 6, let's give it 2 examples. If volts are 6 volts equals, let's call it a current of 3. Call it 3 amps here. 3 amps here. And let's call it 6 amps here. Let's go back to 6 volts, right? 6 volts right here, because it's not going to change. My voltage is not going to change. And that would mean my resistance here would be, what times 3 would get me 6? Would be 2. 2 ohms. Well, and this one would have to be 1 ohm, right? Well, look what's happened here. When my current increased, so from 3 to 6, my resistance had to decrease from 2 to 1. So, and we know that's the case because the voltage kept the same. That's what would have to happen to them. Because I can't change I can't change my volts of battery in a circuit. So we can agree then that my voltage will equal my current times my resistance. That's an equation we can use, and that's an equation you should pay attention to. So we can say V equals I times R. That's how they're related. So if I've kept the voltage the same and my current increases, then my resistance has to decrease. So what are some other relationships that we have noticed? And let's erase this stuff over here so we can write some more equations, because this is the fun part. So what if I wanted to keep my current the same? What if I wanted to keep my current at, let's call current 6. Okay? 6 amps. What did I say if I wanted to make that 6 stay the same one, but I wanted to change my voltage and my resistance, kind of what would happen? And to understand this, your ampage is going to be equal to your voltage divided by your resistance, and I kind of showed you that earlier. So it's going to be equal to your voltage divided by your resistance. If you don't believe me, come over here and look, and this was voltage, right? This was voltage and this was amps. So 6 divided by 2 would get me 3. So it's going to be, let's use if that was 6, then it would have to be 6 divided by 1 would get me 6 divided by 1 would get me 6 amps. Now, this is incorrect, and I hope I've told you enough in class that you have to have the proper units. So 6 volts and 1 ohm. If we were going to bring this down again, though, so if we're going to make this 6 amps and make this 6, let's keep it at 6 volts or whatnot. If this is going to increase, what kind of relationship do these two have in common then? What would happen if I made this 12? What would happen to my 12 volts and I kept 1 ohm the same? Well, my my current would increase too. Same thing over here. Again, remember, what happens if I make my voltage bigger? Well, my current has to increase. Look at the math over here. If I changed my 6 from 6 to 12, what would have to happen to my amps? My amps would also have to go to 12 too. So we can say they have a direct relationship. And remember, whenever we were talking about different kinds of relationship, if two variables are being divided, that means they have a direct relationship. And let's write that out. So the equation we're going to look at now, and we're about to compare the two relationships that we made a second ago, right here. So it's going to be volts over resistance equals current. And we agree with that. And you can say that current and volts have a direct relationship. Because if current increases, then volts also increases. But go back to here. What would happen if again, say my current was whatever number it was, and I increased my voltage or I increased my amps. So this remains 6, but I increased my resistance from 1 to 6 or so. So it was 1. Now it's 6 over 6. Well, what's going to happen to my current? My current is going to be 6 here, but it's going to be 1 over here. Well, what does that mean? That means that current and resistance have an inverse relationship. And that's what we said over here, right? That current and resistance have an inverse relationship. It's illustrated by this equation also. So things to keep in mind, that current and voltage have a direct relationship where one increases, the other one increases, and current and resistance have an inverse relationship when one increases and the one decreases. So current and voltage have a direct, and current and resistance have an inverse. And then finally, the last way we can arrange this equation is going to be rearranging this part right over here, where, well, let's fix that because we need to put this. So that increases, and so does your current. Okay. The final equation is, let's go look right here. If I wanted to get, I got current by itself here, I got voltage by itself here. Oh, by current, I need to put I. That's my problem. Let me fix that. We know it's got to be the letter I. Sorry for the confusion. It's the letter I. If that's been bothering me for the past couple minutes, I apologize. So, what would happen here? So I've got I by itself, I got V by itself, but I don't have R by itself. How would I get R by itself? Well, I would divide I by both sides of the equation. So divide by I, crosses out, and I would get something over I, so V over I equals R. And the same thing, remember, when one thing is being divided by something else, they have a direct relationship. So same thing here. If I increase this, then this has to increase to keep that number the same. So if that was 20 and that was 5, and that would give you, obviously that would give you 4. In order to keep the same ratio, if I increase that to 40, this would have to increase to 10 to keep it the same. So they have a direct relationship. That's pretty much going to wrap up this video over electricity as far as the analogy. Again, the three terms you need to know is current, which is measured with symbolized by I, measured in amps. Voltage, which is the amount being pushed or pulled through by a circuit, is measured in volts, and it's symbolized by the letter V. And resistance is how much